Okay, section 2.3, chapter 2.3, permutations and factorials. Now, this is really, really important. I want to introduce you guys to a really great new math tool that you may have never seen before, but it really is a great tool. It's called a factorial, and it's part of the study of permutations. And just think of like what we were doing in last section with the multiplicative counting principle. So when you're multiplying the number of outcomes for each kind of event, but when you did those examples where we had the events, let's say drawing something without a replacement, or rearranging the letters in a word, how many ways you can arrange the letters in a word. So you notice every time you multiplied by a number, each successive event, the number went down. 5 times 4 times 3 times 2 times 1. Well, you know what? There's a special mathematical operation for that, and it's called a factorial. Okay. So what are we going to be learning here? So we're going to use this to help determine a number of different orders in which we can pick or place a set of items. And this idea of factorial, well, many counting and probability calculations involve the product of a series of consecutive integers, which is what we did in the last section. And a factorial indicates the multiplication of these consecutive decreasing natural numbers. Okay. So how do we read this? Well, we read this as a n factorial. So this is the new notation here, n with this exclamation mark. This means n factorial. And whenever you see this n factorial, n could be any number, a natural number. So n factorial is going to represent this special kind of multiplication, where you have the number that n represents multiplied by the one less than n, then multiplied by n minus 2, multiplied by n minus 3, times so on and so on and so on until you get all the way down to 3 times 2 times 1. Okay, so this factorial idea is a new kind of, like, let's say it's an operation, right? It just tells me the successive multiplication of decreasing natural numbers. Okay, of consecutive decreasing natural numbers. Okay, we're not skipping any numbers here. We're starting from n and we're working backwards all the way back down to 1. Okay, so here let's just do an example of calculating some factorials. So 3 factorial, well, that's simply you take n, which is 3, and you multiply it by every single number, decreasing natural number, or consecutive decreasing natural number. So I multiply it by 2, and then I multiply it by 1 right after that, and that equals 6. So you'll notice in some of your scientific calculators, you will notice that there is a factorial option on your calculator to do this. And you can take full advantage of that. Okay, part B, let's look at another one, 8 factorial. So this is just simply 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, and if the result of this is 40,320. Okay, it's a unique and powerful tool for accounting. Okay, accounting especially without replacement. Okay, that's really important to say. 69 factorial, same idea. You can just express this as 69 times 68 times 67, and so on, times until you get all the way down to 1. So 3 times 2 times 1. And this ends up being a really, really, really big number. It is 1.7112 times 10 to the exponent negative 98. Or sorry, 10 to the exponent 98. So really, really big number. Really big number. Okay. 70 factorial, if you do this on your calculator, you might find an error, not enough memory, perhaps. Or yeah, it's a really, really big number. What about other operations? So we're going to have to know how to divide factorials. Okay, divide factorials. Now you can also do all sorts of neat tricks with factorials as well. Like, for example, 8 factorial. Well, we know 8 factorial is just 8 times 7 times 6, 5, 4, 3, 2, 1, okay? But instead of writing 6 times 5 times 4 times 3 times 2 times 1, I can replace all that with 6 factorial. Because 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which would complete the rest of what I need to do 8 factorial. But why am I writing 6 factorial instead of writing everything expanding everything like 6 times 5 times 4 times 3 times 2 times 1? Well, the reason why I'm doing that is because if you notice, I am dividing by 6 factorial on the bottom. Okay, and just like you would with algebraic expressions and numerical fractions, you can make cancellations. So I can cancel the top and the bottom like so. Okay, now that would result in a nice answer for us. 8 times 7, 56. Okay, let's look at another one. 83 factorial over 79 factorial. Same idea. 83. 83 factorial is 83 times 82 times 81 times 80. And once you get to 79, I'm just going to write 79 factorial. Okay. Now remember, if 70 factorial in the calculator gave me an error, 83 factorial will also give me an error. It's just too big. But by doing some simplifications, I can avoid having to do that big number calculation on my calculator, because I'm just going to write 83 factorial out by writing the first four terms, or first four numbers, and then multiplying by 79 factorial afterwards. Because on the bottom, I have 79 factorial as well. So then I can just reduce it by canceling the same numbers on the top and the bottom, just like you would any numerical fraction. And then all I have to do on my calculator is multiply these four numbers. And when I do that, I get 44,102,880. Okay. What about a little bit of kind of expression like variables and things like that? Well, you're going to have to know how to do this in this course as well. So n plus 1 over n plus 1 factorial, you notice that maybe there is some kind of way I can cancel this out from the top and the bottom. Well, let's just see how that looks like. So n plus 1 is on the top. On the bottom, I can express n plus 1 factorial as n plus 1 times, what will be the next term? Well, I have to subtract 1 from this, so n plus 1 minus 1 is n, and then times n minus 1 times n minus 2 times n minus 3 and so on. But instead of doing all that, I'll just say n factorial. Okay, so n plus 1 factorial is just n plus 1 times n factorial. It's kind of like I'm just removing the first number out of the whole factorial operation, which I can do. Okay, but by doing this, I can cancel the factor on the top with the factor on the bottom, or the bracket on the top and the bracket on the bottom, and I'm left with just 1 over n factorial. All right. Again, H, let's look at another example of some algebraic manipulation with these factorial expressions, variables, and whatnot. So n factorial, the idea is I want to try and cancel something on the bottom with this n minus 1 in brackets. So if I write n factorial, I can write it as n times n minus 1 factorial. Okay, n minus 1 factorial contains all the other numbers, n minus 1, n minus 2, n minus 3, all the way down to 1. And then I have n minus 1 factorial on the bottom. Same factors in the top and the bottom, which I can cancel. And my final result is n. So we now so far have learned how to do a new operation, a factorial, and how to manipulate expressions and quotients and fractions with factorials in them. So let's actually apply this operation, this factorial operation, with an example and a kind of a arrangement problem. So in how many ways can you arrange the letters in the word math? So just like in the last lesson, we looked at how many ways we could arrange the letters in the word money. So I'm just taking one here that says math. Okay, so how many positions do we have? Well, I'm going to say that there are 4 letter positions. Okay, so one first position I have 4 options. In the second position I have 3 options. In the third letter position I have 2 options. And in the last one I just have 1 option. I'm just talking about the letters here, right? So when I have 4 options for the first one, I can choose M, A, T, or H. If I chose T, then I have M, A, and H for this option. And if I have chose A, then I don't have M and H left here, and then I have 1 left here for the last one. So to calculate the number of possible arrangements, it's just the multiplicative counting principle, right? It's just 4 times 3 times 2 times 1. But now I can simply just, instead of using the multiplicative counting principle, I can express this as 4 factorial. Okay, this number of arrangements is called a permutation, right? How many permutations of the word and letters in the word math can I do? So there are 4 factorial ways, possible arrangements, to arrange the 4 letters in the word math. Okay, so here there are 24 possible arrangements. Okay. Looking at my next example, the senior choir has rehearsed 5 songs for an upcoming assembly. In how many different orders can their choir perform the songs? Well, for the first song, they have 5 songs to choose from, so there's 5 possibilities, which every time they sing a song, you reduce the number of songs available. So for the second song, there's only 4 possibilities. 3 possibilities for the third song, 2 possibilities for the fourth song, and then finally, there's only 1 song left, 1 possibility for the fifth song. So I can express this using the multiplicative counting principle. So I can say 5 times 4 times 3 times 2 times 1. But this is also just the same way of saying 5 factorial. And 5 factorial is 120. And what that means, there are 120 possible song orders. It's as simple as that. So you can imagine how factorials are a nice simple way of expressing the multiplicative counting principle when you're reducing consecutive natural numbers by 1. Now imagine a bit larger problem when you're doing, like, let's say 100 all the way to 1. Well, that makes a factorial much easier than doing 100 multiplications. So that's why we have this kind of operation available to us. Let's look at example number 4. So a librarian wants to display 8 books on a bookshelf. So let's circle that 8 books. That might be very important. There are 3 books. Circle that as well. So 3 books by Joseph Boyden, and the rest are by different authors. In how many ways could he arrange the books if the Boyden books are side by side? Ah, interesting. Okay. So 8 books on a bookshelf, 3 are by Joseph Boyden, but they're going to be side by side. How do I deal with a problem like this? Well, we could treat the Boyden books as 1 unit. 1 unit. So if I have 8 books arranged on the bookshelf, so 1, 2, 3, 4, 5, 6, 7, 8, I can treat the 3 Boyden books as 1 unit. So I'm going to just circle 3 spots like this. Okay. And how many ways are there to arrange the Boyden books? Well, there are 3 factorial ways to arrange them. Okay. So really what we have now is just 6. There are only 6 units to order here. Okay, we have 1, 2, 3, 4, 5, and the 3 Boyden books kept together is the 6th one. Okay, so there are 6 factorial ways to order these 6 units. And there are 3 factorial ways to order the Boyden books amongst themselves. So how do we calculate the total number of arrangements? Well, if I use the factorials combined with the multiplicative counting principle, I can say 6 factorial times 3 factorial equals 4,320 arrangements for the books on the shelf. Okay. Now, what if they're not side by side? Well, then we can use, again, what we call an indirect method. Okay, so we already know part A, that there are 4,320 arrangements of the Boyden books being side by side on the shelf. So if they're not side by side, then I'm going to just subtract the number of possibilities from part A from all the possibilities. Okay, so what are all the possibilities? All possibilities mean that there are 8 books that we have to put in order. Okay, so that means there are 8 factorial ways to arrange those books. Okay, and so that means to find the number of ways to arrange the books so that the Boyden books are not side by side. Well, there are 8 factorial total possibilities minus the 6 factorial and 3 factorial possibilities of the books being beside each other. So that gives me an answer of 40,320 minus 4,320, which is 36,000 possible orders or possible ways to arrange these books so that the Boyden books are not beside each other. Okay, so permutations. This is all what we've been doing here is just permutation. So permutation of an n distinct items is an arrangement of all the items in a definite order. The total number of such permutations is denoted by n permutation, npn, or sometimes p of n and n. Okay, so there are n possible ways of choosing the first item, n minus 1 ways of choosing the second item, n minus 2 ways of choosing the third, and so on. Applying the fundamental counting principle says that a permutation of n items and n ways to arrange them is just given by n factorial. That's all the factorial is. It's just a permutation. How many ways are there to arrange n items in from choosing n items, right? So in example number 5 here, in how many different orders can 8 nominees for student council give speeches at an assembly? Okay, so we have 8 nominees. And so basically I'm asking, what is the permutation of 8 nominees arranged in 8 ways? Okay, and that's simply 8 factorial, okay, which is 40,320. So there are 40,320 possible speech orders. So there are 40,320 possible speech orders. Now you can ask me, well, how can that be? It's just 8 nominees. How can there be 40,320 ways? Well, I mean, it's a very complicated problem. If these are all distinct, they're all individual, they're all unique nominees. So you can write down 8 names and try to arrange 8 names in any way you want. You'll find that there are really 40,320 possible combination or permutations. So the number of permutations of R items taken from n distinct items is a little bit different. So meaning, if the 8 nominees are not arranged in exactly 8 ways, so what if n and n? What if these 2 numbers are different? Then it's a slightly different permutation problem. So we now describe it as n distinct items, so n distinct number of nominees. But instead of arranging them in 8 ways, we're going to arrange them in a smaller number of ways. Okay, so n has to be bigger than r. So the number of ways, number of items, is n, and the number of ways to arrange those items is r. Okay, and to deal with a problem like this, simply says, well, the multiplicative counting principle, we take n times n minus 1 times n minus 2 times n minus 3 times all the way down to n minus r plus 1. Okay, because you're not arranging them all, you're just arranging them n minus r plus 1 as my final number. Or you can follow this nice factorial formula where you have n factorial. So the number of ways you can arrange n items n ways divided by the n minus r factorial, where you have just a factor that takes care of the removes the other possibilities, and just does it in r ways or r items. Okay, it's not so important to understand where this formula comes from, but we're just going to use it to determine the permutations of r items from n distinct items. Okay, let's go through an example. Maybe it might be clear when we do. So here in a card game, a player is dealt a face-down reserve of 13 cards that can be turned up one at a time used during the game. How many different sequences of reserve cards could a player have? Okay, so we're talking about how many items? Well, a deck of cards, n is 52 cards. So n is going to be 52. My apologies, ink here. So n equals 52. A deck of 52. So 52 in the deck. And for some reason my ink is spilling here on the screen. So R, we're saying, is 13. So we have 13 cards in this reserve dealing, okay, dealt reserve cards. So I'm interested in figuring out NPR. So how many ways are there to arrange a deck of 52 cards in such a way that I'm choosing 13 of them? Okay, so this is really 52 choose 13. Okay, and so using my factorial formula for permutation, so 52 factorial divided by 52 minus 13 factorial, and which is 52 factorial divided by 49 factorial. Okay, maybe it was just a zoom in problem here. Okay, so taking care of this equals 52. Oh, same problem again. I'm not sure why this ink is doing 52 times 51 times 50 times 49 factorial. I'm going to stop at the factorial because I can cancel it with the 49 factorial on the bottom. Cancel, cancel. And 52 times 51 times 50 is 132,600. So there are 132,600 possible sequences of cards. So basically saying, taking my deck of 52 cards, how many ways can I deal a hand of 13 cards? There are 132,600 ways.